All right. So this problem set can be found on our Canvas page. And the first question I want to look at is question number 1. So question number 1 asks us, what's the difference between heat and thermal energy? Well, I'm going to just kind of discuss this one with you guys. You know, thermal energy is the energy that's associated with the motion of particles, right? Whereas heat is the flow of thermal energy. So heat, we use the term heat, you know, in our everyday language, and heat represents the flow of thermal energy, but thermal energy is the energy associated with the motion of particles. So let's write that down. Thermal energy is energy associated. I think of the quickest definition I can come up with. It's energy associated with motion of particles, and heat is the flow of thermal energy, right? And you know, in terms of thermal energy, one of the classic questions that gets asked in chemistry is, you know, what has more thermal energy, a boiling coffee cup full of water, or you know, a swimming pool full of water at 60 degrees Celsius? Well, the answer is going to be the swimming pool, right? Because you add up all the energy of all the particles in your system. Anyhow, the next one is just kind of a few fill in the blanks. It says temperature. Temperature is just a measure of thermal energy. So the way that we measure thermal energy is using temperature scale. I get two things on my mind here, don't I? Thermal energy. Okay. The sum of the potential and kinetic energies of all particles present in a system, that's the internal energy of the system. So internal energy, just getting some more definitions out of the way here. A property that depends on the state of the system, regardless of how that state was achieved, is called a, who could tell me what the answer to this one is? If you watched my videos for sections 6.1 and 6.2, you would have seen this definition repeated several times throughout those videos. Anybody tell me what that would be? No, it's not a phase state. Okay, so this is a definition that you all need to be fully aware of. This is in section 6.1 exactly. This is a state function. A state function. Okay. The property depends only on the state. Doesn't matter how we got there. For example, you know, what are some state functions? Volume, temperature, pressure, enthalpy. Those are all state functions. Whereas work, for example, W, is not a state function. Anyhow, number 5, a process in which thermal energy is transferred from the system to the surroundings, meaning that you're releasing heat from the system. Who could define what that would be? When heat is being released by the system into the surroundings. What kind of process would that be? Exactly. Thanks, Christian. That's an exothermic process, right? Exothermic, thermic. And then the next one says a process in which thermal energy is transferred from the surroundings to the system. That's an endothermic. Thermic. And when we have an exothermic reaction, that's when our delta H is going to be negative, our delta H of our reaction. And when the delta H of our reaction is positive, that's an endothermic reaction. This next question, number 7, is a definition that you should all be aware of, and that's what a joule is equivalent to. And 1 joule is equal to 1 kilogram per meter squared per second squared. If you've never taken physics before, you probably haven't heard that, but that's something that you're going to want to be aware of. All right, I wanted to skip ahead a little bit here to question number 10. Okay, just discussing some more forms of energy. So this is question number 10. This match Each type of energy with its definition provided in the table below. Not all the options will be used. So this comes right back to the beginning of chapter 6 when we discussed the different types of energy. And we said thermodynamics is the interconversion or the study of the interconversion between heat and different forms of energy. And then thermochemistry, of course, is the study of the heat associated with chemical reactions. But anyhow, before we can get into thermodynamics, we need to know, what are the different types of energy. The first one is energy that comes from the sun. So the energy that comes from the sun, that would be radiant energy, right? Radiant energy. Okay. The next one is the energy associated with the random motion of particles. Who could tell me what that one would be? Energy associated with motion, the random motion of atoms or molecules. We looked at this already today. No, it's not going to be. So associated with the random motion of atoms or molecules in a system, that would be thermal energy. Thermal energy. Okay, next one. If you have your mic on, can everybody check to make sure their microphone is off because somebody has it on? The next one is the energy stored within the bonds of substances. That would be potential energy. So their potential energy that's stored in bonds. Energy. The next one is the energy stored within the collection of neutrons and protons in the atom. So where are the neutrons and protons found? They're found in the nucleus. Nucleus. So that would be nuclear energy. Nuclear energy. And the next one is the energy stored in an object due to its position. So due to its position relative to other objects, that would be potential energy. So potential energy. Now, at the very beginning of chapter 6, the author of our textbook goes over all the different types of energy. So it might be a good idea to review that. Well, now I want to skip ahead to question number 12. I think this would be a great question for the next exam. It says here that above minus 196 degrees Celsius, liquid nitrogen boils and becomes gaseous, right? It gets converted to gaseous nitrogen. Consider a tank of nitrogen existing at 26 degrees Celsius. So that means that all of the nitrogen will be in the gaseous phase, right? None of it will be liquid because in order for it to be a liquid, it would have to be below 196. Now, this is where it gets important. It says where 84.65 joules of heat are transferred from the surroundings to the tank. If the walls of the tank do 27 joules of work on the nitrogen, what is the change in energy? So we're looking for the change in energy. And you might remember that we looked at delta E, and this is a way of rewriting the first law of thermodynamics, that delta E is equal to heat plus work. Now, everybody can add or subtract two numbers. So what you have to interpret here is what is the sign of Q and what is the sign of W, right? Because Q is heat and W is work. And you can see that those two words are in here. We have heat and we have work. So what is the sign? Well, let's take a look at the heat first. So let's rewrite our equation. Delta E is equal to Q. So if 84.65 joules of heat is transferred from the surroundings into the tank, that's the system. That means that heat is going into the system from the surroundings. And so in this case, the sign of our Q is going to be positive. So it's going to be positive 84.65 joules, right? If heat was leaving the tank and going out into the surroundings, then the Q would be negative. But since the Q or the heat is being absorbed by the system, it's positive 84.65. And then we need to decide what's the sign of W. Are we going to add, positive 123.7, or are we going to add negative 123.7 joules? And it says here 123.7 joules of work on the nitrogen. Okay, so the tank is doing work on the nitrogen. If the nitrogen was doing work, then the sign of the W would be negative. But since the work is being done on the system, right, it's being done on the nitrogen inside the tank, that means the sign of our W is going to be positive as well. And so we write 123.7 joules. So really, nothing more than adding those two numbers together. Nothing more than that. So when you punch those into your calculator, remember that you have two decimal places here and only one decimal place here. So your final answer can only be reported to one decimal place, and it ends up being 208.4 joules. So 208.4 joules. All right, let's skip ahead to question number 13. It says here that you've got a tank. A tank of ultra-high purity helium arrives with 6,852.68 liters of helium and an internal pressure of 17.692 atmospheres. After being attached to a gas chromatograph for a couple of months, the volume has decreased to 4,398.22 liters. The temperature and pressure remain constant. Calculate the work done in kilojoules. So what you need to understand here, it's just kind of the wording. It says after being hooked up to a gas chromatograph. A gas chromatograph is just an instrument that's used to separate molecules in the gaseous phase, so you can compare, you can separate them based on their polarity, which is something that we'll look at more in chapter 12. Anyhow, it's basically hooked up to an instrument that uses the helium. So for this question, since we're being asked to calculate the work, we're going to need an equation for work, which is work is equal to the negative of pressure times delta V. Well, we've been given our pressure, which is 17.692 atmospheres. And then to calculate delta V, remember that delta V is going to be equal to the final volume minus the initial volume. And the change in our delta V is going to be, let's see, our final volume is what? 4,398.22 liters, subtract 600.68 liters, like that. So when you punch all that spinach into your calculator, you get some really wacky, you get some wacky units here. So you multiply that out, you get 43,424 ATM liters. Now, we're trying to calculate work in kilojoules, but luckily they've given us a conversion factor to convert atmosphere liters into joules. And so if we multiply that by the conversion factor, 101.3 joules per 1 ATM liter, that would give us the answer in joules, but we know that there are 1,000 joules in 1 kilojoule. And so we would divide that whole thing by 1,000. And when you do that, you end up with, or I ended up with 4.399. I guess you could even have more sig figs than that, but anyhow, times 10 to the 3 kilojoules. So there we go. So that equals, that's the same thing as saying 4,399 kilojoules, like that. So there's our final answer. All right, so again, it's just the last two questions have been, more than anything, they've been a matter of interpreting the problem, right? Reading the problem and interpreting that problem. Okay, I want you guys to think about the next question, which is question 1 of the section about enthalpy. I'm going to let you read that question and see if you can come up with an answer. All right. So it says determine whether the following reaction is endothermic or exothermic and determine the sign of delta H. Well, we already discussed delta H's sign earlier today with respect to when a reaction is endothermic or exothermic. And we said that when delta H is positive, when it's positive, that's an endothermic reaction. And when delta H is negative, we said that's an exothermic reaction. Okay. Now, what you see here is that we have this equation hydrogen plus bromine, okay? These are the reactants, aren't they? These are the reactants. And we end up with hydrogen bromide plus 48.7 joules of heat being released. So these are the products. So you can think of heat as being a product, right? Let's circle that. You can say heat is a product. And so if heat is a product, that means that heat is being released. Therefore, heat is being released. So who could tell me what the sign of delta H would be in this case? Would it be positive or negative? Would this be an endothermic or an exothermic reaction? Exactly. Jamil says it's exothermic, and the H or delta H is going to be negative. Ashlyn says the same thing, and they're both correct. So when heat is a product, that means that this is an exothermic reaction because heat is being released. So delta H is negative, therefore exothermic. Okay, and again, that's because heat is being released. Okay, heat is a product of this reaction. Okay, let's take a look. Let's try question number 2. I'm not a mega fan of these type of questions, but just to kind of walk you through it, if you've been trying some of these questions at home for your own personal edification. It says here, you decide to conduct an experiment using a laser to detect the change in enthalpy from 3 different reactions. Let's just try the first one. Reaction 1 conditions are this. You neutralize. It's a neutralization reaction between hydrochloric acid and sodium hydroxide. This reaction was run at atmospheric pressure, 1 atmosphere, at 20 degrees Celsius, so around room temperature. Under these conditions, the change in enthalpy was negative 56.5 kilojoules. It's an exothermic reaction, right? Heat was released. And you see that heat is a product over here for this complexation reaction. Draw the enthalpy diagram for the first reaction and determine whether the reaction is endothermic or exothermic. Well, what it's saying here is that we want to draw the reaction in terms of its energy, right? What has more energy, or what has less energy, I should say? Is it the reactants or the products? Well, if my reactants, let's say they have a certain amount of energy, okay? There's a certain amount of energy associated with the reactants. There's also a certain amount of energy associated with the products. But remember, the energy of the universe remains constant. Energy is not going to be created or destroyed. It can be interconverted between forms, different forms, but we're not going to destroy energy. So if there's a certain amount of energy associated with the reactants, and there's a certain amount of energy associated with these products right here, what else do we get besides these products, water and sodium chloride? We also end up with heat as being a product. That means that in order to have a balanced equation, right, in order to balance this equation overall in terms of its energy, the products must have less energy than the reactants, right? Because in order to balance this, I had to add heat, right? I had to add that heat. So that tells us that our starting materials, the HCl plus the sodium hydroxide, are higher in energy, aren't they? Right? These are our reactants. It tells us that our products, water and sodium chloride, are lower in energy. These are our products. And the delta H of the reaction is going to be negative 56.5 kilojoules, right? That ends up being lost after you combine these two reactants. Not only do you form these products, but you end up forming some heat. And if you've ever tried a neutralization reaction in the lab, which I'm sure many of you have, you'll notice that it's an exothermic reaction. You can actually feel, the flask or the vessel, whatever you choose to do the reaction, and you can feel it warming up. Anyhow, 1 second here. Let's take a look at one more of these really quickly. I said this is the only one we do, but take a look at one more and then we'll get into something different. Let's take a look at C because this is a different type of reaction. It says here reaction 3 conditions, complexation of magnesium 2 plus with EDTA. The reaction was run with an atmospheric pressure of 1 atmosphere and 20 degrees Celsius. Under these conditions, the change in enthalpy was measured as 23.0 kilojoules. Notice that the sign is positive. So that tells you that this is what? This is an endothermic reaction. Draw the enthalpy diagram for this reaction and determine whether it's exothermic or endothermic. Well, we already did the first part. We know it's endothermic. Well, we want to take the same approach as the last time. Look, there's a certain amount of energy associated with the reactants, and there's a certain amount of energy associated with the products. Well, in order to balance this out in terms of energy, you have to add energy to the reactants in order for them to have the same amount of energy as the product. So that tells you these reactants are lower in energy. So that means that our reactants in this case are going to be down here. So we'll put MgCl2 plus EdTA. Okay. So these are our reactants. Our products, write those down. Our Mg MgEdTA 2 minus plus 2Cl minus. And our delta H is going to be positive this time. It's going to be 23.0 kilojoules because heat has to be absorbed by the reactants in order to form the product. So that's an enthalpy enthalpy diagram. And anyhow, I'm not going to ask you to draw an enthalpy diagram in a multiple choice quiz, obviously, or to fill it out, but you should have some kind of knowledge or understanding of what the heck is going on here. Okay, let's switch gears and let's talk about calorimetry for a little bit. Now we're on to something completely different. So this is calorimetry. This is, I think, section 6.3 or something in our textbook. Explain the difference between specific heat capacity and heat capacity. I think the easiest way to define these are in terms of their units. Specific heat capacity, that's little c, and that's equal to joules per gram degrees Celsius. Now I could write out a whole wordy answer here, but specific heat capacity is the amount of energy that it takes to raise 1 gram of a substance by 1 degree Celsius. Okay, that's what specific heat capacity is. Maybe I could make sure that my degree Celsius is a little bigger. Whereas heat capacity is big C, and that's equal to joules per degree Celsius. So heat capacity is associated with any amount of a substance, and it's the amount of heat required to raise that amount of a substance or that substance by 1 degree Celsius. You probably also remember a formula that we're going to need to solve question number 2. It says, what is the heat capacity? Right? They're asking you, what is big C if 8.17 kilograms of aluminum, or what is the heat capacity, rather, of 8.17 kilograms of aluminum? And they give you the little c, right? This is the specific heat capacity. Now, what do you notice is that C, big C, heat capacity is equal to mass times specific heat capacity, isn't it? I'll prove it to you. If you convert this 8.17 kilograms into grams, and how can we do that? Well, we know that 1 kilogram has 1 times 10 to the power of 3 grams. We can just write out 8.17 times 10 to the 3 grams multiplied by 0.900 joules per gram degrees Celsius. Look at what happens. Move that over here a little bit. Look at what happens when we do that. Well, the units of grams cancel out, and we're left over with joules per joules per degree Celsius, which are the units of heat capacity. So when we multiply out all that spinach in our calculator, we end up with an answer that should have 3 sig figs, right? Because we have 3 sig figs here in our mass, and we have 3 sig figs in our specific heat capacity. So when I multiplied that out in my calculator, I got 7.54 times 10 to the 3 joules per degree Celsius. We'll put here 7.54 times 10 to the power of 3. All right, let's try another one. That's from the calorimetry section. An unknown hunk of lead. I don't know why they didn't just write an unknown piece of lead. It's kind of strange. An unknown piece of lead is found to have a heat capacity. So this is our big C, a heat capacity of 66.82 joules per degree Celsius. What's the mass of the hunk of lead if you have a specific heat capacity of 0.158 joules per gram degree Celsius? I'm going to give you a second to see if you can figure that out. Give you a minute to try to figure that one out. Hey, can you ask them to stop pounding on the floor, please? It's really loud. Okay. All right. Sorry, my kids are dancing upstairs, and it sounds like the world is coming to an end down here in the basement. All right, did anybody get an answer for this one, for the mass of the piece of lead? Even an approximate answer? You just did the math in your head, maybe? Or could anybody tell me what formula I would use to solve this problem? Yeah, Jamil put 423. That's what I got. I got 423 grams, right? And the formula that he used to solve that problem is that heat capacity is equal to mass times specific heat capacity. Therefore, from that, he could derive that mass is equal to heat capacity divided by specific heat capacity. So we took the heat capacity, which is 66.82 joules Celsius, divided by 0.158 joules per gram degrees Celsius. Look at this. Isn't this a beautiful thing? Joules cancel, as do degrees Celsius, and we end up with grams. And so we end up with a mass of 423 grams. There we go, 423 grams. So just manipulating this formula. So what does that tell you? You need to know what the units of specific heat capacity are, of heat capacity. You need to know this formula. And with that, you'd be able to answer all the last three questions. Question number 4 is maybe, kind of designed for students that have trouble deriving formulas. But I would think that, if you're given a formula like Q is equal to MC times delta T, that you would be able to derive, well, Q is equal to M times C times delta T. But you should be able to derive, M and say M is equal to Q divided by C delta T. C is equal to Q divided by M times delta T, and delta T is equal to Q over M times C. You should be able to derive those in 1 second, okay? I'd say that that's the most basic algebra that you would look at, in university. All right, let's take a look at another problem. This is question number 5. It says, suppose you are attempting to heat 48.0 grams of mercury from 22.6 to 56 degrees Celsius. How much heat is required to accomplish this? And they give you the specific heat capacity of mercury. Well, in order to solve this problem, you're going to use the formula Q, which is heat, is equal to mass times specific heat times delta T. We are given a mass, which is 48.0 grams. We're given the specific heat capacity, 0.139 joules per gram degree Celsius. And we're going to calculate our delta T from here, right? Our delta T is going to be equal to our TF minus our TI. We're starting out with a final temperature, which is 56.0 degrees Celsius, and we're subtracting 22.6 degrees Celsius. When you shorten all that, you get that Q is equal to 48.0 grams times 0.139 joules per gram degrees Celsius multiplied by 33.4 degrees Celsius. Look at this. The units of temperature cancel, as do the units of mass, and you're left over with joules, which are units of energy. And they want you to solve the problem for the number of joules. So when you punch all that spinach into your calculator, you end up with an answer of 223 joules. Like that. Give me a thumbs up if you feel like you did that one, or you could nail that one pretty quickly. Anybody feel confident about that one? Okay, Good. If you're feeling confident about that, I'm going to give you 60 seconds to try to solve number 6. Hey Siri, set a timer for 60 seconds.
Your timer is set for 1 minute.
Okay, who's got an answer? It's like Jeopardy. Who's got an answer for this one? Blake's got 10.6. Josh has got 11 grams. Somebody else has 10.6. You're all in the right vein, that's for darn sure. How did these students solve this problem? They said, okay, well, I know that Q is equal to M times C times delta T. I'm given my Q, right? I'm given my Q. I'm going to go right like this. I'm given my C, and I'm given my delta T. You don't even have to calculate delta T. They just tell you the temperature goes up by 26 degrees Celsius. And so all we have to do is isolate M. And we did that a few minutes ago. We said that M is equal to Q divided by C times delta T. Then we just fill in the blanks, right? We have our Q, which is 106.0 joules. We divide that by our specific heat capacity, 0.385 joules per gram degrees Celsius, and we multiply that by delta T, which is 26.0 degrees Celsius. Look at this. Units of joules cancel, as do degrees Celsius, and we're left over with our mass in grams. When you punch that into your calculator, you end up with 3 sig figs, right? So the students who put 3 sig figs, they're all correct, right? You have 4 sig figs here, 3 here, and 3 here. So the answer can only have 3 sig figs, and the answer is going to be 10.6 grams. There we go. Great job, you guys. Excellent. Maybe I should set some more Siri timers as we move forward. Okay, another question. Let's try number 7. Let's give it the old college try and do one for Clyde. Okay. Here we go. If you add 652 joules of heat to 50 grams of ethanol, what would the temperature change be? Okay, let's try it. Let's do the old Siri timer here. We'll do one more like that. Hey Siri, set a timer for 1 minute.
Okay, your timer is set for 1 minute.
Grab a pencil and give it. All right, let's give it the old go here. What did somebody write? Sierra, Jennifer, Brianna, Blake. Well, jeepers, y'all wrote the same thing, so I'm hoping that's the right answer. Okay, let's give it a shot. They all use the formula Q is equal to M times C times delta T. We are looking for delta T. And when we solve for delta T, we get the delta T is equal to Q divided by M over C, or M times C. Our Q is 652. joules. Our mass is 50.0 grams, and our specific heat capacity is 2.46 joules per gram degrees Celsius, like that. Let's double check our units. Joules, grams cancel, we're left over with degrees Celsius. And we end up with 5.30 degrees Celsius, right? We should have 3 sig figs. We have 3 here, and 3 here. We're doing multiplication and division. And so our final answer will also have 3 sig figs. So we'll put that down, 5.30 degrees Celsius. Okay, let's try the next question. This is dealing with stoichiometry of thermochemical equations. Let's read through the problem together. It says potassium permanganate, that's this guy here, KMnO4. Potassium permanganate is a strong oxidizer, which produces a purple flame when reacted with glycerin. The balanced reaction is shown below. So we get a beautiful balanced equation. 14 moles of potassium permanganate plus 4 moles of glycerin gives you 7 moles of potassium carbonate, 7 moles of manganese 3 oxide, 5 moles of carbon dioxide, and 16 moles of water. And this is an endothermic reaction, right? You have to put in 6,557.66 kilojoules of energy. But remember, that value, this value right here, and I can't stress this enough, this delta H is associated with this specific action, okay? These two things belong to each other. We were made for each other, right? Anyhow, these are made for each other. They go together like a hammer and a nail. Socks and shoes, they go hand in hand like the rhythm and blues, okay? Anyhow, it says here, calculate the mass of each product formed when 1,801 kilojoules of heat is transferred in 4 separate reactions, okay? Assume that each reaction goes to completion. So what they're saying here is if you released, or sorry, in this reaction that's in the blue box, okay, this guy right here, you released this much heat. Now, what if you only released this much heat? Not as much heat, is it? Right? It's not as much. So they're asking us, okay, well, if this much heat was released, how much calcium carbonate would be reacted, or sorry, would be formed, rather. Okay? So how much potassium carbonate would you form if you release this much heat? Let's see how we would do this. Okay, we should solve this using dimensional analysis. If we were to release 1,801 kilojoules, and we know that our reaction releases 6,557.66 kilojoules for every how much potassium carbonate? For every 7 moles of K2CO3. Look, if we were to stop right there, which we're not going to, but kilojoules would cancel out, and you'd end up with the amount of heat released, or sorry, you'd end up with the amount of moles of potassium carbonate that is formed when you burn and you release 1801 kilojoules of heat. Okay, so another conversion factor, aren't we? Right? Now we know that in 1 mole of potassium carbonate, and I've gone ahead and looked up the molar mass already, there's 138.2 grams of potassium carbonate. Now look at it. We have the amount of heat released cancels with the amount of heat released from our reaction in the blue boxes. When we balance that out, that's 7 moles of potassium carbonate. Okay? But then if we multiply it by the molar mass of potassium carbonate, that's going to give us the amount of potassium carbonate that's formed. When we do that, we get 265.7 grams of potassium carbonate, 265.7. So with that in mind, I want to skip ahead all the way to C. I'm only going to try a couple of these because they're the same thing over and over and over. But I'm going to give you a second to see if you can solve for C, for the amount of carbon dioxide that's formed. Again, I'll give you a minute to do it. Hey Siri. Hey Siri. Set a time. Set it. Oh, that's off. Set it. Hey Siri. Set a timer for 60 seconds.
Your timer is set for 1 minute.
All right, let's give it a shot. Does anybody have an answer for this one? Yeah, the students that are answering are definitely in the right vein. They said, okay, we're going to start it with the 18.01 kilojoules of heat that was released. And I know that I get my 6,557.66 kilojoules. What a strange number, huh? For every 5 moles of CO2. Where did I get that from? Let's go up here. Look, starts with B, ends with balanced equation. That's right. The balanced equation, there's 5 moles of CO2. And I know that in 1 mole of CO2, that there are 44.01 grams of CO2. Double check our units. Kilojoules, moles of CO2 cancel. We're left over with grams of CO2, and we get 60.43 grams of CO2. So 60.43 grams of CO2. Before I go on, sometimes I don't read the entire chat. It's kind of hard to do 2 things at once. But I noticed, Autumn, I'm going to mention you here just for a second. I noticed that in the last question, my students were plugging in answers or whatever. And Autumn said, she said one thing and then she said, oh, I just redid it. And I got the right question. I'll put a thumbs up by that one, right? Why did Autumn get the right answer? The answer is yes, but she redid it. So look, let me just kind of put a little disclaimer here for all my students, okay? Something I don't think I've ever brought up with you guys, but it's probably something that you learned in junior high and high school, and you've heard in other university courses, is always double check, okay? Always double check yourself. Like this morning, I was preparing for the next lecture that I was going to do, and I was looking at an equation called the Clausius-Clapeyron equation, and I'm going to teach it to you later on next week. You're not called out at all, okay? Not at all. You're called out in a good way. Okay. Anyhow, I was looking at that equation and I did it, and I got an answer after I solved the problem that I was going to look over with you guys. And the answer wasn't unreasonable, right? 5.21 is not an unreasonable answer, but it's not the right answer. So I double checked my calculation. I was like, oh, like now I have a different answer. So I triple checked it and I figured out that I'd made a little mistake in the first time. So remember, lots of people make mistakes. I make mistakes every class, right? Anyhow, normal. Anyhow, so always double and triple check. Okay, the last thing I wanted to look at with you guys in terms of review, I think, was just a couple questions that deal with Tess's law. Again, I guarantee you that I'm going to put a question that deals with Tess's law on the final exam. Okay, so you can hitch your wagon to that. It's going to happen, right? Okay, so let's see here if we can calculate. It says here, calculate delta H for the reaction between carbon sulfide and oxygen. So carbon sulfide plus oxygen gives you carbon dioxide and sulfur dioxide. It's a perfectly balanced equation. And we want the delta H for this reaction, don't we? We're looking for the delta H of this reaction. But what did we say earlier today? The enthalpy is a state function. It doesn't matter how you get there. The pathway is not important, okay? And so whether we did this reaction in one step or whether we did it in a series of steps, okay? If we take these reactions, A, B, and C, and we tally them up in such a way that they give us this equation here in the red box, okay? And then we tally up the delta H's, we're going to end up with the delta H of that reaction. So let's see how we would do that. Now, if you examine equation A, B, and C, the first thing I'm going to do is I'm going to look for my carbon sulfide. The only place I see carbon sulfide is right here, okay? There's none here and there's none here. So that means that I have to take equation C and I have to reverse it, don't I? Okay, now what happens when you reverse an equation? When you reverse an equation, you also reverse the sign of delta H. So we're going to take this whole thing and basically multiply it by -1. It's a way of, just saying we're reversing it. So let's rewrite equation C. So we're going to put equation C will be this. We're going to start with carbon sulfide. In the liquid phase, it's going to produce carbon plus 2 moles of sulfur. And now our delta H is going to be equal to -87.90 kilojoules. So again, all I did was reverse that equation. What else? I need to have oxygen as a reactant, don't I? Well, let's see. I have oxygen here and I have oxygen here, so I'm not really sure which one of those to manipulate next. What else? I see that I need to have carbon dioxide as product. I need to have carbon dioxide as a product, and I need to have sulfur dioxide as a product. Well, I need carbon dioxide as a product. The only place I have carbon dioxide is right here, and I need 1 mole of it. So that means I'm not going to change this equation in any way, shape, or form, am I? So I'm just going to rewrite that equation. I'm going to say equation A, I haven't done anything to it. I'll put carbon in the solid phase plus oxygen in the gaseous phase gives me CO2 gas. My delta H of A isn't going to change. It's negative 393.5 kilojoules. What else do I need? I need to have 2 moles of sulfur dioxide. The only place I see sulfur dioxide is here, but there's only 1 mole of it, and so I'm going to multiply equation B by 2. Let's do that. So now I have 2 moles of sulfur in the solid phase plus oxygen gives me 2 moles of SO2 gas. Delta HB, have to multiply 296.8 negative multiplied by 2, so that gives me negative 593.6 kilojoules. Now, before I start tallying up delta H's and just skip to the end and write down the final answer, let's be sure that I manipulated my equations correctly. So I'm going to tally up all 3 of these, right? I'm going to look at the reactant side, everything that's the reactant, and then I'm going to look at the product side, everything that's a product, and anything that's the same on both of those sides, I can cancel out. Well, looky. What's the same on both sides? Carbon solid is the same on both sides, as is solid sulfur on the same on the both sides. So I've got CS2, my carbon sulfide. I've got oxygen. Did I not multiply something by 2 here? Yeah, I didn't multiply my oxygen by 2, so I'm missing a 2 there. Anyhow, I've got a total of 1, 2, 3 moles of oxygen, don't I, as a reactant? So let's write that down. The total is going to be CS2 liquid plus 3 O2 gas produces. I've got carbon dioxide and 2 moles of sulfur dioxide. So let's scribble that down. We've got CO2 gas plus 2 moles of SO2 gas. Hess's law is a beautiful thing. Now what I'm going to do is I'm going to tally up all these. Now, obviously, I've gone ahead and done that ahead of time. There we go. Thanks, Sierra. Good. And when you tally up negative 87.9, negative 593, and negative 393.5, you tally up all those numbers, and you get negative delta H of your reaction is equal to negative 1075 kilojoules. So negative 1075 kilojoules, just like that. Would you guys like to try one more? Or if compounds are in different states, no, they would not cancel out, Jennifer. They have to be in the same state in order for them to cancel out. Okay, if you guys want to try one more, I guess I'm taking up more time on practice today than I thought, but hey, this is the land of the free, right? So let me just tell you, this is a little bit late, but if there's anybody out here who's watching the YouTube video of this, what I would recommend is that you, read the question with me during the video, pause the video, try the question your own self, and then look at the solution. Don't just watch me solve problems, because of course it's going to make sense when you watch me solve a problem, but you want to be able to solve it yourself. Okay, that's enough of me lecturing you about how to study. It says here, calculate delta H for this reaction, generating chlorine trifluoride. So we have ClF gaseous plus fluorine gas gives us chlorine trifluoride gas. And we're given all 3 of these beautiful equations, and we want to end up with that reaction that I have highlighted in yellow, and we want the delta H of this reaction is what we're looking for, aren't we? Well, the first thing I notice here is the chlorine trifluoride is only found right here. This is the only place you find chlorine trifluoride is in equation C. And so we're going to have to take equation C, we're going to have to reverse it so that it will be a product, right? So we've got to multiply by -1, and we have 2 moles of it, so we're going to have to divide by 1/2. So I'm going to multiply this whole thing by -1/2. And then when I rewrite equation C, I'm going to end up with 1/2 mole of Cl2O plus 3/2 OF2 gaseous produces ClF3 gas plus O2 gas. Then when I recalculate my delta H for C, I'm going to give it a negative sign and divide it by 2. I end up with -266.7 kilojoules, like that. Okay, so I took care of that. Then for the ClF is the starting material. The only place that I see that is right here. Okay, I don't see it anywhere else in here. So I'm going to have to take equation B, and I'm going to have to multiply it by 1/2, right? I have to divide everything by 2. So let's do that. So we're going to say we've got ClF gaseous plus 1/2 mole of oxygen produces 1/2 mole of Cl2O plus 1/2 mole of OF2 gaseous. And then the delta H for that one, when I divide that in half, I get that my delta HB is 102.8 kilojoules. Okay, then from equation A, what do I see in equation A? It's the only place that I have the fluorine, isn't it? Okay, it's the only place I have F2, but I have 2 moles of it, and it's a product. So I have to reverse that to make it a reactant. So I'm going to multiply that whole thing by -1/2. So let's write down what we're going to have for equation A. It's going to be equal to F2 in the gaseous phase plus 1/2 mole of oxygen. It's going to give us OF2 in the gaseous phase, like that. And when I multiply that by -1/2, delta HA, I've done it here. Where is it? I get 24.7 kilojoules. Now, again, before you get all excited with yourself and start adding up the delta H's, let's double check to make sure that we manipulated our equations correctly. So we're going to look at all the reactants, and then we're going to examine all of the products. And if there's anything that's the same on both sides, we're going to cancel it out. So look, first thing I notice is the chlorine oxide. So I have 1/2 mole of chlorine oxide. I have 1/2 mole of it here. Let's see. Here I have 3/2 OF2. What's 3/2? 1.5, right? You take 3 and divide it. You take $3 and divide it by 2, you get $1.50. Okay, so I have 3/2 OF2. Here I have 1 OF2 and 1/2. You take $1 and you add $0.5 $1. What do you got? $1.50. Good. So these are all going to cancel out. Okay. I have 1/2 mole of oxygen here, 1/2 mole here. 1/2 and 1/2 makes a whole, and that's going to cancel it with 1 whole mole of oxygen. And then looky what I've got left over. I've got my ClF plus my fluorine gives me ClF3. So let's jot that down just to be sure. We've got ClF in the gaseous phase plus F2 in the gaseous phase produces ClF3 in the gaseous phase. I tally up all those delta H's. I've already gone ahead and done that. And when I did that, since they all end with a decimal, where am I here? They all end with 1 decimal place, 1 decimal place, 1 decimal place. My final answer will have 1 decimal place. And I ended up with -139.2 kilojoules. So the delta H of the reaction is equal to -139.2 kilojoules. Give me a thumbs up if you follow me on Hess's law and manipulating equations to get an overall, get a delta H for a reaction. All right, thanks, Blake. Good, thanks, Brianna. Excellent. Wunderbar, as we say in German. Okay, let's take a look at question 6, section 6, sorry, just for a second. I think the first question is worth discussing. It says, why does an element in its standard state have an enthalpy of formation of 0. Delta HF naught is equal to 0 for an element in its standard state. Well, the reason why is because if an element is in its natural state, it takes no energy to form it, right? Because it is in its natural state, and it takes no energy to form that state, to form the natural state. Okay. For example, if you have, pure nitrogen, N2, in the air, it takes no energy to form N2 because it's the most stable state. Same thing with O2, right? Same thing with just potassium in its natural state. The heat of formation is 0, right? It takes no energy to form it because that's how it's naturally found. All right, well, we're going to use this table, and there's actually a value missing here. I noticed it this morning, and I'll write it down here. That would be for H2 gas. You need that it's 0 kilojoules per mole. Anyhow, so we're going to use all of these standard enthalpies of formation to solve. Let's try question number 2. Okay. It says here in 1918, Fritz Haber was awarded the Nobel Prize in Chemistry for the synthesis of ammonia from its elements. That synthesis is shown here. Nitrogen plus 3 moles of hydrogen gives you 2 moles of ammonia. The reaction occurs above 400 degrees Celsius to produce gaseous ammonia. Then you cool it to obtain liquid ammonia. The balanced reaction is here. Calculate the delta H of the reaction to 3 significant figures. Well, in order to solve this problem, we're going to use the formula that delta H of our reaction is going to be equal to the sum of the stoichiometric coefficients multiplied by the delta H formation of the products minus the sum of the stoichiometric coefficients multiplied by the delta H of formation of the reactants, right? And the reason why it's easy to memorize this equation because you're subtracting the HF for the reactants. That means you're putting a negative sign on the formation. So you're breaking apart the reactants, right? You're breaking these apart, and then you're forming these, or this in this case, because there's only one of them. Well, with all of that in mind, let's plug in some numbers here. So the delta H for this reaction, which is called the Haber process, we take the delta HF of formation of our product. We only have one product. It's ammonia. Let's look it up. And you can see that ammonia has a delta HF of negative 45.9. But remember, we have 2 moles of it. So we're going to say 2 multiplied by negative 45.9 kilojoules per mole. Okay, we have no other products. Then we're going to subtract the delta H of formation of nitrogen and hydrogen. Well, the easy thing here is that both of them are 0, aren't they, right? The delta HF of nitrogen is 0, and for hydrogen is 0. So we're going to subtract 0 kilojoules per mole. And so hopefully you see where we're going with this. The delta H naught of this reaction is going to just equal 2 times negative 45.9. So that gives us negative 91.8 kilojoules. All right, and there is our answer. So negative 91.8 kilojoules for that reaction. Okay, let's try one more. Do one more problem in this vein, and that's question number 3. So it says here, the thermal decomposition of potassium carbonate occurs at over 1200 degrees Celsius. The balanced reaction is given to you right here, and it asks you to calculate delta H for this reaction, delta H naught for this reaction. I'm going to set a timer for 2 minutes. I want you to take 2 minutes and try this one yourself, and then we'll reconvene. Hey Siri, set a timer for 2 minutes.
Your timer is set for 2 minutes.
Oops, I didn't mean to do that. Anyhow, another alarm's going to go off because I pressed repeat instead of stop. Okay, anybody get an answer for this one? I'm curious. Any of my students got an answer? Okay, well, let's try it here. We're going to use the same formula. We're going to say the delta H of our reaction is going to be equal to the sum of the heats of formation of our products. So we've got carbon monoxide and oxygen. We'll go look up carbon monoxide, which is right here, negative 110.5. Oxygen is O2, so that's obviously 0. We'll plug those in. So we've got negative 110.5 kilojoules per mole. Okay, plus 0. Oh, I forgot about the potassium. Oops. Neon's losing it. There we go. Plus potassium. Potassium is also 0 because it's in its pure state. Okay, so we get the first part done. And then we're going to subtract the delta HF of the reactants. And it's potassium carbonate. Let's go up here and look up potassium carbonate in the table. Right here, it's negative 1150.2. So subtract negative 1150.2 kilojoules per mole, like that, and we get that our delta H of our reaction is equal to 1039.7 kilojoules. Okay, and there we have it. Okay, like that. So we'll put 1039.7 kilojoules, like that. Okay. So the first reaction that we looked at in this section, in question number 2, this is an exothermic reaction because heat is released. And then this is an endothermic reaction because heat was absorbed and their delta H has a positive value. All right, there's only one more question I wanted to look at in this problem set, and it's question number 6. Question number 6, it says, why do most compounds have a negative enthalpy of formation? If you go back to this table, you look at most of the compounds, right, you see that their signs are negative, right? We have all negatives here, we have a negative here, except for ozone has a positive, but most are negative. And there's a good reason for that, and it's because heat is released when compounds are formed from their elements in their standard state. The compounds are more stable than the elements. So let's write that down. Because heat is released when most compounds are formed from their elements. The compounds are more stable than elements in their standard state.